Most people think natural disasters come out of nowhere. But in reality, the Earth is giving us signals all the time. We just don't always know how to read them. In this video, I'm going to explain what's really happening beneath the surface, why it matters, and what it means for people who live there. This is Geohazards Explained. Right now, a quiet update out of the Pacific Northwest just made Cascadia look sharper, more segmented, and potentially more complicated than the simplified, one continuous megathrust picture most people have in their head. In the last few months, researchers released a new high-resolution offshore map of the Cascadia megathrust, showing it may be divided into at least 4 structural domains. And a separate study refined where the locked zone likely sits, the part of the fault that stores strain for the next great earthquake. And if you live anywhere from Vancouver Island to Northern California, this matters, because the difference between alarming and catastrophic can come down to where the fault is locked, how it breaks, and how much of it breaks at once. This is not a prediction video. No one can tell you Cascadia will rupture. This is a hazard update. New research, what it changes, what stays the same, and what you should realistically do with the information. We will cover the new offshore imaging that suggests at least 4 segments in the Cascadia's megathrust, a 2024 coupling model that estimates where the locked zone boundaries are and how much moment is accumulating, a recent Cascadia slow slip and tremor episode, what it is and why scientists pay attention to it, and the historical context, the 1700 orphan tsunami record, and why Cascadia is still one of North America's biggest geologic threats. Cascadia is a subduction zone. The Juan de Fuca plate and related plate fragments is diving beneath the North American plate. According to Oregon's emergency management guidance, the Cascadia subduction zone is roughly 700 miles long and sits about 70 to 100 miles offshore. The last full-margin great earthquake occurred on January 26, 1700, estimated around magnitude 9.0, and it produced a tsunami recorded in Japan. They also emphasize that a major Cascadia event could mean minutes of strong shaking and a major tsunami threat along the coast. Now, here's the recent event that flew under the mainstream radar. A documented episodic tremor and slip episode, often shortened to ETS, in the northern Cascadia region. The Pacific Northwest Seismic Network posted a log entry describing an ETS event in the southern Vancouver Island, northern Washington area, with dates August 6, 2024 to September 6, 2024. They describe it as a normal tremor sequence lasting about a month, and they compare it to earlier episodes in 2023. That's not a big earthquake you feel. This is the fault quietly slipping at depth over days to weeks, accompanied by tiny signals called tremor. ETS is not the megathrust breaking in the catastrophic way. It's deeper, slower movement that scientists monitor because it helps map where the fault is behaving differently, and some research discusses how slow slip may transfer stress toward the locked zone. Now, to the big research update. In June 2024, a Science Advances paper presented regional-scale seismic imaging across the Cascadia margin, spanning roughly approximately 900 kilometers from Vancouver Island toward the California border. And it argues the Juan de Fuca plate is fragmenting within the seismogenic zone, creating structural domains that line up with long-discussed rupture segmentation. The University of Washington Earth and Space Sciences summary of that work says the new map hints the megathrust fault is not just one continuous structure, but is divided into at least 4 segments. And they highlight a key point. Off Washington and Oregon, one segment appears shallower and smoother, which could make it more likely to slip more coherently. And they note the geometry may extend the fault eastward beneath the Olympic Peninsula. This matters because a shallower, smoother interface can change how shaking is distributed on land and what the tsunami source looks like offshore. Segmentation tells you the fault isn't uniform. But the next question is, which parts are locked right now? A Journal of Geophysical Research, solid Earth paper first published October 24, 2024 by Sherrill, and colleagues tackled exactly that, estimating the upper and lower boundaries of the locked zone and how creep transitions below it. Key findings they report for Cascadia include: the locked zone is west of the coastline and about 10 kilometers up dip of the slow slip zone along much of the margin. It is widest in northern Cascadia, reported as roughly 25 to 125 kilometers wide, extending to about approximately 19 kilometers depth, and narrowest in central Cascadia, reported as 0 to 70 kilometers wide. They estimate moment accumulation rates that are equivalent to something like magnitude 8.71 to magnitude 8.85 for 300 to 500-year earthquake cycles. This is not tomorrow. This is a way of expressing accumulated strain and potential release. They also discuss steep creep gradients immediately below the locked zone, consistent with propagating creep behavior. Here's the breaking update takeaway. What did not change? Cascadia remains capable of a major megathrust earthquake and damaging tsunami. That's been true for decades, and emergency management agencies still plan around that scenario. What did change? We now have stronger evidence that Cascadia is not a simple, uniform fault. The new imaging provides a higher resolution structural framework and supports the idea of persistent segmentation, boundaries that may sometimes slow or steer ruptures. The locked zone boundary modeling refines where strain is likely accumulating and highlights strong regional differences along the margin. This cuts both ways. Segmentation can sometimes mean ruptures break in smaller pieces, but it can also mean certain sections, especially smoother, more coherent regions, could behave as high-consequence patches if they rupture strongly. So it's not safer or more dangerous in a simplistic way. It's more specific, and specificity is what improves hazard models. Let's anchor this in history. Oregon's emergency management page summarizes that the last great Cascadia earthquake occurred on January 26, 1700, estimated magnitude 9.0, and that it caused parts of the coastline to drop several feet, generating a tsunami that crossed the Pacific. Evidence preserved in Japanese records of a destructive tsunami arriving without a local earthquake. That's the key psychological trap with Cascadia. Because the fault is offshore, and because it can be quiet for long stretches, people treat it like a theory instead of a schedule. But the geologic and historical record says, Cascadia has produced many great earthquakes over thousands of years, and the 1700 event is a real dated example of what the system can do. So what should you actually do with this update? If you're inland, Seattle, Tacoma, Portland, Vancouver, your main risk is long-duration shaking, infrastructure disruption, and the cascading effects. Know your building type, secure heavy furniture, and have supplies ready. If you're coastal, your biggest immediate threat after a big quake is the tsunami. In a Cascadia scenario, you may not get much time. If you feel long, strong shaking, go. Don't wait for an alert. And keep an eye on ongoing research updates that feed into hazard maps and building codes, Pacific Northwest Seismic Network tremor, and ETS monitoring. It's not a warning system, but it's a key diagnostic, an official preparedness guidance in your area. Geologic hazards can't be eliminated, but they can be understood. And when we understand how the Earth works, we make better decisions about where we live, how we build, and how we prepare. If this helped you see the ground beneath your feet a little differently, consider subscribing for clear, honest explanations of Earth's most powerful processes. This is Geohazards Explained, and see you in the next one.